Business analytics refers to the practice of using data, statistical and quantitative analysis, and predictive modeling techniques to gain insights and make data-driven decisions in business. It involves the collection, processing, analysis, and interpretation of data to support business decision-making processes. Business analytics can be applied to various areas of business, including marketing, finance, operations, and human resources, among others. The goal of business analytics is to help organizations improve their performance and competitiveness by identifying patterns, trends, and opportunities in their data. The components of business analytics typically include data collection. This involves collecting relevant data from various sources, such as databases, spreadsheets, websites, social media platforms, and other sources. The data can be in structured or unstructured form. Data processing. Once the data has been collected, it needs to be cleaned, organized, and formatted in a way that is suitable for analysis. This can involve tasks such as data cleansing, data transformation, and data integration. Data analysis. This is the process of examining the data to uncover patterns, trends, and insights that can be used to inform business decisions. This can involve using statistical analysis, data mining techniques, and machine learning algorithms to extract insights from the data. Data visualization. After analyzing the data, it is important to present the findings in a way that is easy to understand and visually appealing. Data visualization tools can be used to create charts, graphs, and other visualizations that help stakeholders understand the insights. Business intelligence. This refers to the use of analytics to support business decision-making processes. Business intelligence tools can be used to create reports and dashboards that provide real-time insights into key business metrics. Illustration. Let's say a retail company wants to improve its sales performance. It can use business analytics to achieve this goal. The company collects sales data from various sources, including point-of-sale systems, online orders, and customer feedback. This data is processed and analyzed to identify patterns and trends in customer behavior, such as which products are popular and which promotions are effective. The company then uses this information to create targeted marketing campaigns and promotions that are more likely to resonate with customers. Data visualization tools are used to create easy-to-understand reports and dashboards that provide insights into sales performance and help the company make data-driven decisions. Cloud computing. Models of cloud services in cloud computing. Cloud computing is a technology that allows users to access computing resources such as servers, storage, applications, and services over the internet on demand, without the need for on-premise hardware and infrastructure. Cloud computing is provided by cloud service providers who own and operate the infrastructure and offer different models of cloud services. The models of cloud services in cloud computing are Infrastructure as a Service, IaaS. This is a cloud computing model in which the cloud service provider offers virtualized computing resources such as servers, storage, and networking infrastructure to users. Users can deploy and manage their own applications, operating systems, and databases on the cloud infrastructure provided by the cloud service provider. Platform as a Service, PaaS. This cloud computing model provides a platform for users to develop, run, and manage their own applications without having to manage the underlying infrastructure. The cloud service provider provides a platform with pre-built tools and services such as development frameworks, databases, and web servers that users can leverage to build their applications. Software as a Service, SaaS. In this cloud computing model, the cloud service provider offers complete software applications that are accessed and used by users over the internet. Users do not need to install or manage the software application, as it is provided as a service by the cloud service provider. Illustration. Suppose a company wants to move its IT infrastructure to the cloud. With IaaS, the company can rent virtual servers, storage, and networking from a cloud service provider and run its applications and databases on the cloud infrastructure. With PaaS, the company can use the cloud service provider's platform to develop and deploy its own applications without worrying about managing the underlying infrastructure. With SaaS, the company can use cloud-based software applications such as email, CRM, or accounting software that are hosted and maintained by the cloud service provider. For model of adoption of analytics in organizations in India. The adoption of analytics in organizations in India typically follows the following model. Initial awareness. In this stage, organizations become aware of the potential benefits of analytics and start to explore how analytics can be used to improve their business operations. This stage is usually triggered by external factors such as market competition or changes in customer behavior. Pilot projects. Once an organization decides to adopt analytics, it typically starts with small-scale pilot projects to test the feasibility and effectiveness of analytics in their business processes. Pilot projects are usually implemented in areas such as marketing, customer service, or supply chain management. Capability building. Once the pilot projects are successful, organizations focus on building internal capabilities to support the adoption of analytics. This involves hiring and training staff with the necessary skills to use analytics tools and technologies, developing data management systems, and establishing processes and governance frameworks for data analytics. Deployment. After building internal capabilities, organizations start to deploy analytics across various business functions and processes. Analytics is integrated into decision-making processes and used to support strategic planning, operational efficiency, and customer engagement. Optimization. As analytics becomes a part of the organization's culture, it continually improves and optimizes its analytics capabilities. This involves monitoring the performance of analytics systems, refining analytics models and algorithms, and integrating new data sources and technologies to improve the accuracy and effectiveness of analytics. Illustration. For example, a retail company in India may become aware of the potential benefits of using analytics to improve its marketing campaigns. It may then conduct a small-scale pilot project to test the feasibility of using analytics to identify customer preferences and target marketing messages. Once the pilot project is successful, the company may focus on building internal capabilities by hiring data analysts and investing in analytics tools and technologies. It may then deploy analytics across various business functions such as supply chain management, customer service, and inventory management. As the company's analytics capabilities mature, it may continually optimize its analytics systems by refining its algorithms, integrating new data sources, and developing more sophisticated analytics models to improve its business performance. 5. The steps of creating an analytics culture in organizations. Creating an analytics culture in organizations involves a series of steps that includes the following. Define analytics strategy. Define a clear analytics strategy that aligns with the organization's overall business strategy. This includes identifying the key business questions that analytics can help answer, setting specific analytics goals, and identifying the data sources needed to support analytics initiatives. Develop analytics capabilities. Develop the necessary capabilities within the organization to support analytics initiatives. This includes hiring data analysts, investing in analytics tools and technologies, and developing data management systems and processes to support analytics activities. Promote analytics awareness. Educate employees across the organization about the value of analytics and how it can be used to improve business operations. This includes providing training programs and workshops to employees at all levels of the organization to improve their analytics skills and knowledge. Foster data-driven decision-making. Encourage a data-driven decision-making culture within the organization. This includes promoting the use of data and analytics in decision-making processes and ensuring that decisions are based on reliable data and insights. Embed analytics in operations. Embed analytics into the organization's day-to-day operations. This involves integrating analytics into business processes and workflows, and ensuring that analytics insights are regularly shared with stakeholders and decision makers. Continuously improve analytics capabilities. Continuously improve the organization's analytics capabilities by monitoring performance, refining analytics models and algorithms, and integrating new data sources and technologies to improve the accuracy and effectiveness of analytics. Measure the impact of analytics. Measure the impact of analytics initiatives on the organization's overall business performance. This includes tracking key performance indicators, KPIs, and regularly reporting on the ROI of analytics initiatives. Illustration. For example, a manufacturing company wants to create an analytics culture to improve its production processes. It starts by defining a clear analytics strategy that identifies key business questions related to production processes, sets specific analytics goals, and identifies the data sources needed to support analytics initiatives. The company then hires data analysts, invests in analytics tools and technologies, and develops data management systems and processes to support analytics activities. It also provides training programs and workshops to employees at all levels of the organization to improve their analytics skills and knowledge. The company encourages a data-driven decision-making culture by promoting the use of data and analytics in decision-making processes and ensuring that decisions are based on reliable data and insights. It embeds analytics into production processes and workflows and regularly shares analytics insights with stakeholders and decision makers. The company continuously improves its analytics capabilities by monitoring performance, refining analytics models and algorithms, and integrating new data sources and technologies to improve the accuracy and effectiveness of analytics. It also measures the impact of analytics initiatives on its overall business performance by tracking KPIs and regularly reporting on the ROI of analytics initiatives. 6. Data analytics applications in HR, marketing, operations, and finance. Data analytics has a wide range of applications across various business functions, including HR, marketing, operations, and finance. HR. Data analytics can be used in HR to improve talent acquisition, employee retention, and workforce planning. It can help identify the most effective recruiting sources, analyze employee turnover patterns, and identify skills gaps in the workforce. HR analytics can also be used to monitor employee performance, identify training needs, and improve employee engagement. Marketing. Data analytics can be used in marketing to improve customer segmentation, targeting, and personalization. It can help analyze customer behavior, preferences, and purchase history to identify new marketing opportunities, optimize marketing campaigns, and improve customer experience. Operations. data analytics can be used in operations to improve efficiency, reduce costs, and optimize supply chain management. It can help identify bottlenecks in production processes, predict equipment failures, and optimize inventory management. Finance, data analytics can be used in finance to improve financial forecasting, risk management, and fraud detection. It can help analyze financial data to identify trends, forecast revenue and expenses, and optimize cash flow. It can also be used to detect fraudulent activities and prevent financial losses. Illustration. For example, a retail company can use data analytics across various business functions. In HR, data analytics can be used to analyze employee turnover patterns, identify skills gaps in the workforce, and improve employee engagement. In marketing, data analytics can be used to analyze customer behavior and preferences, identify new marketing opportunities, and optimize marketing campaigns. In operations, data analytics can be used to optimize inventory management, identify bottlenecks in production processes, and predict equipment failures. In finance, data analytics can be used to forecast revenue and expenses, optimize cash flow, and detect fraudulent activities. By leveraging data analytics across various business functions, the company can improve its overall performance and achieve its business objectives. 7. Big data, uses of big data. Big data refers to extremely large data sets that are too complex for traditional data processing methods to handle. The term is also used to describe the technologies, tools, and practices used to manage and analyze these large data sets. Big data can be used in various industries and business functions to gain insights, make data-driven decisions, and improve business performance. Some of the key uses of big data include business intelligence. Big data can be used to extract valuable insights from large and complex data sets to support business intelligence and decision-making processes. It can help identify patterns and trends in customer behavior, market trends, and internal operations. Predictive analytics. Big data can be used to develop predictive models that can help businesses forecast future trends and outcomes. This can help businesses identify potential risks and opportunities and make proactive decisions to mitigate risks or capitalize on opportunities. Personalization. Big data can be used to develop personalized experiences for customers. By analyzing customer data, businesses can understand individual preferences and behaviors, and tailor products and services to meet their unique needs. Operational efficiency. Big data can be used to improve operational efficiency by optimizing supply chain management, reducing waste, and improving production processes. Risk management. Big data can be used to identify and manage risks in various industries, including finance, healthcare, and cybersecurity. By analyzing large and complex data sets, businesses can identify potential threats and take proactive measures to mitigate them. Healthcare. Big data can be used in healthcare to improve patient outcomes and reduce costs. By analyzing patient data, healthcare providers can identify patterns and trends in disease progression, predict potential health risks, and develop personalized treatment plans. Illustration. For example, a retail company can use big data to gain insights into customer behavior, market trends, and internal operations. By analyzing large and complex data sets, the company can identify patterns and trends in customer behavior, such as buying patterns, preferences, and demographics. This can help the company develop personalized experiences for customers, optimize marketing campaigns, and improve customer satisfaction. Big data can also be used to improve operational efficiency by optimizing supply chain management, reducing waste, and improving production processes. By analyzing data from various sources, the company can identify inefficiencies in the supply chain, such as bottlenecks or delays, and take proactive measures to address them. In addition, big data can be used to develop predictive models that can help the company forecast future trends and outcomes. For example, by analyzing sales data and market trends, the company can predict future demand for its products and adjust its inventory levels accordingly. Overall, the use of big data can provide businesses with a competitive advantage by enabling them to make data-driven decisions, optimize operations, and improve customer experiences. 8. Vs of big data. The Vs of big data are a set of characteristics or properties that define the nature and challenges of big data. The Vs are: volume refers to the massive amount of data that is generated and collected on a daily basis. Big data is typically characterized by its size, with data sets ranging from terabits to exabits. Velocity refers to the speed at which data is generated and needs to be processed. In many cases, big data is generated in real time or near real time, requiring immediate processing and analysis. Variety refers to the diversity of data types and sources that make up big data. Big data can include structured data, such as data in databases, as well as unstructured data, such as social media posts, emails, and videos. Veracity refers to the accuracy and reliability of data. Big data can be noisy, incomplete, or inconsistent, making it challenging to ensure data quality. Value refers to the potential business value or insights that can be derived from big data. Big data can provide valuable insights into customer behavior, market trends, and operational efficiency, among other things. Variability refers to the dynamic nature of big data, which can change rapidly and unpredictably. This can make it challenging to manage and analyze big data effectively. Visualization refers to the ability to present and interpret big data visually, using charts, graphs, and other visual tools. Visualization can help make complex data more accessible and understandable. Illustration. For example, a social media platform like Twitter generates massive amounts of data in real time, including tweets, retweets, and comments. This data is highly varied in nature, including text, images, and videos, and can be noisy and incomplete. However, by analyzing this data, businesses can gain valuable insights into customer behavior and sentiment, as well as track the success of their social media campaigns. The velocity of data generated on Twitter can also pose a challenge, as businesses need to be able to process and analyze the data in real time to respond to customer feedback and make timely decisions. The value of this data is significant, as it can help businesses improve customer engagement and loyalty, increase brand awareness, and drive sales. By visualizing this data using tools like charts and graphs, businesses can gain a better understanding of customer sentiment and preferences, and make data-driven decisions to improve their marketing strategies. 8. Technology infrastructure required for business analytics in organizations. To implement business analytics in organizations, there are several technology infrastructure requirements that need to be in place. Some of the key infrastructure requirements for business analytics include: data storage. A robust data storage system is essential for business analytics. This may include relational databases, data warehouse, or big data platforms like Hadoop or Spark. The storage infrastructure should be able to handle large volumes of data and provide high performance and scalability. Data integration. Business analytics requires data from multiple sources, which needs to be integrated and consolidated before it can be analyzed. Integration tools like ETL, extract, transform, load, software or API, application programming interface, can be used for this purpose. Data processing. Once data has been integrated, it needs to be processed and transformed to extract meaningful insights. This may involve data mining, statistical analysis, or machine learning algorithms. Analytics tools. Various analytics tools are used for data analysis and visualization, including statistical analysis software like R or Python, dashboarding tools like Tableau or Power BI, and machine learning frameworks like TensorFlow or Keras. Cloud infrastructure. Cloud-based infrastructure like Amazon Web Services, AWS, Google Cloud Platform, GCP, or Microsoft Azure can be used to host and manage the entire analytics infrastructure, including data storage, processing, and analytics tools. Security. Data security is critical for business analytics, and organizations must have proper security measures in place to protect their data. This may include firewalls, encryption, and access controls. Human resources. Finally, an organization must have skilled personnel with expertise in data analytics, data science, and data engineering to manage and operate the analytics infrastructure effectively. In summary, implementing business analytics in organizations requires a robust technology infrastructure that includes data storage, integration, processing, analytics tools, cloud infrastructure, security, and skilled personnel. Unit 2. 1. Objectives of exploratory data analysis. The objectives of exploratory data analysis, EDA, are to gain a deeper understanding of the data, identify patterns, and generate hypotheses for further analysis. More specifically, the main objectives of EDA include: identify the underlying structure of the data. EDA helps to identify patterns and relationships in the data, including trends, clusters, and outliers. Test assumptions. EDA can be used to test assumptions about the data, including normality, linearity, and independence. Determine the distribution of the data. EDA helps to identify the distribution of the data and determine whether it is skewed or has heavy tails. Detect outliers. EDA helps to identify extreme values or outliers in the data, which can be a source of error or signal important information. Explore the relationship between variables. EDA can be used to explore the relationships between different variables and identify any correlations or causal relationships. Identify missing or erroneous data. EDA can help to identify missing or erroneous data, which can be a source of bias or error in the analysis. Generate hypotheses. EDA can be used to generate hypotheses about the data, which can be tested using statistical methods. Overall, the main objective of EDA is to gain a better understanding of the data and use this understanding to guide further analysis and decision making. EDA is an essential step in any data analysis project and can help to ensure that the analysis is based on a solid understanding of the data. 2. Methods of exploratory data analysis. There are several methods of exploratory data analysis, EDA, which can be used to gain a deeper understanding of the data and identify patterns and relationships. Here are some of the commonly used methods of EDA. Summary statistics. This involves computing summary statistics such as mean, median, mode, standard deviation, and variance to describe the data. Data visualization. This involves plotting the data to identify patterns and relationships visually. Some common visualization techniques include histograms, scatter plots, box plots, and heat maps. Dimensionality reduction. This involves reducing the dimensionality of the data to simplify analysis and visualization. Principal component analysis, PCA, and TSNE, T-distributed stochastic neighbor embedding, are some of the commonly used techniques for dimensionality reduction. Outlier detection. This involves identifying observations that are significantly different from the rest of the data. Some of the commonly used techniques for outlier detection include box plots, Z-scores, and clustering. Correlation analysis. This involves identifying the relationship between variables in the data. Correlation coefficients such as Pearson's R, Spearman's rank correlation, and Kendall's tau can be used to measure the strength of the relationship between variables. Cluster analysis. This involves grouping similar observations together based on their attributes. Cluster analysis techniques such as k-means, hierarchical clustering, and scan, density-based spatial clustering of applications with noise, can be used for this purpose. Association rule mining. This involves identifying patterns in the data where one event is likely to lead to another event. Association rule mining techniques such as a priori and FP growth can be used for this purpose. Overall, these methods of EDA can be used to identify patterns and relationships in the data, detect outliers, reduce dimensionality, and generate hypotheses for further analysis. 3. Exploratory data analysis and confirmatory data analysis. Exploratory data analysis, EDA, and confirmatory data analysis, CDA, are two different approaches to data analysis. EDA is an approach used to summarize, visualize, and explore data to understand its characteristics, identify patterns, and generate hypotheses. It involves looking at the data without any preconceived notion of what might be present in the data. EDA aims to explore the data and generate insights that can be used for further analysis. EDA is usually done at the beginning of a data analysis project. CDA, on the other hand, is an approach that involves testing hypotheses that are preconceived based on the research question being asked. CDA aims to confirm or refute hypotheses using statistical methods. CDA involves selecting appropriate statistical models, estimating parameters, testing hypotheses, and drawing conclusions. CDA is usually done after EDA to confirm or refute the hypotheses generated during EDA. In summary, EDA is an exploratory approach to data analysis, while CDA is a confirmatory approach to data analysis. EDA is used to generate hypotheses and insights, while CDA is used to confirm or refute these hypotheses using statistical methods. Both approaches are important in data analysis and can be used in conjunction to obtain a complete understanding of the data. 4. Concepts association, correlation and causation with examples. Association, correlation, and causation are concepts commonly used in data analysis and statistics. Association refers to the presence of a relationship between two variables. It means that the occurrence of one variable is related to the occurrence of another variable. For example, there is an association between smoking and lung cancer. However, this does not necessarily mean that smoking causes lung cancer. Correlation refers to the strength and direction of the relationship between two variables. It measures the extent to which the two variables are linearly related. For example, there is a positive correlation between height and weight. This means that as height increases, weight also tends to increase. However, correlation does not imply causation. Causation refers to the relationship between cause and effect. It means that the occurrence of one variable directly causes the occurrence of another variable. For example, smoking causes lung cancer. However, establishing causation requires careful consideration of confounding variables, the temporal order of events, and the strength of the association. Here are some examples that illustrate the difference between association, correlation, and causation. Example 1. There is an association between ice cream consumption and the incidence of sunburns. People tend to consume more ice cream in the summer when they are exposed to more sunlight, and they also tend to experience more sunburns during this time. However, there is no correlation between ice cream consumption and sunburns because the two variables are not linearly related. There is no causation because ice cream consumption does not directly cause sunburns. Example 2. There is a positive correlation between education level and income. People with higher levels of education tend to earn more money. However, this does not necessarily mean that education causes higher income. Other factors such as work experience, job market conditions, and personal motivation may also contribute to higher income. Example 3. There is a causal relationship between smoking and lung cancer. Studies have shown that smoking increases the risk of developing lung cancer. This is supported by the temporal order of events. Smoking occurs before lung cancer, and the strength of the association. Smokers are much more likely to develop lung cancer than non-smokers. 5. Cronbach's alpha and its uses. Cronbach's alpha is a statistical measure used to assess the reliability or internal consistency of a scale or test. It is named after the American psychologist Lee Cronbach, who developed it in 1951. Cronbach's alpha measures the degree to which the items in a scale or test are related to each other, and therefore measure the same underlying construct. It ranges from 0 to 1, with higher values indicating greater internal consistency. A value of 0 indicates no correlation between the items, while a value of 1 indicates perfect correlation. Cronbach's alpha is commonly used in various fields such as psychology, education, and social sciences to assess the reliability of questionnaires or surveys. It is useful in situations where a set of items is designed to measure a single construct or variable. For example, it can be used to assess the reliability of a personality test, where multiple items are used to measure a single personality trait. Cronbach's alpha can also be used to assess the reliability of composite scores, which are created by combining multiple measures of a construct. For example, if a company wants to measure employee engagement, they may use multiple items such as job satisfaction, organizational commitment, and motivation to create a composite score. Cronbach's alpha can be used to assess the reliability of this composite score. In summary, Cronbach's alpha is a statistical measure that is used to assess the internal consistency or reliability of a scale or test. It is a useful tool for researchers and practitioners to ensure that their measures are reliable and valid, and that they accurately reflect the underlying construct of interest. 6. For reliability analysis output. Infer the Cronbach's alpha value from the given table. Infer the item total statistics table, just inferring procedures. Here are the general procedures to infer the Cronbach's alpha value and item total statistics table from a reliability analysis output. Cronbach's alpha. Look for a table that provides the Cronbach's alpha value for the scale or test you are analyzing. The table should have two columns, Cronbach's alpha, and no of items. The Cronbach's alpha value is typically listed under the Cronbach's alpha column. Item total statistics. Look for a table that provides the corrected item total correlation coefficients for each item in the scale or test. This table should typically have at least 3 columns, item, Cronbach's alpha if item deleted, and corrected item total correlation. To infer the item total statistics table, follow these procedures. Identify the table that provides the corrected item total correlation coefficients for each item. Check that each item has a corrected item total correlation coefficient greater than 0.2. This indicates that the item is contributing to the overall reliability of the scale or test. Check that the Cronbach's alpha if each item is deleted is not substantially higher than the overall Cronbach's alpha value. If it is, this indicates that the item may not be measuring the same construct as the other items in the scale or test. If necessary, remove any items with low corrected item total correlation coefficients or high Cronbach's alpha values if deleted, and rerun the reliability analysis to obtain a new Cronbach's alpha value and item total statistics table. 7. From multiple regression SPSS output. Write regression equation. Explanatory power of the model. Infer the R-square value. Infer ANOVA table and coefficients table in regression model analysis times validate the overall fitness of the model, just procedures. Here are the general procedures to obtain and interpret the relevant information from a multiple regression SPSS output. Regression equation. Look for the coefficients table in the regression output. Identify the row labeled constant and the rows labeled with the names of the predictor variables. Write down the regression equation as follows. Y is equal to b0 plus b1 x1 plus b2 x2 plus bn asterisk xn. Where y is the predicted value of the dependent variable, x1 x2, xn are the predictor variables, b0 is the constant, and b1 b2, bn are the coefficients for each predictive variable. Explanatory power of the model. Look for the model summary table in the regression output. Identify the row labeled R-square. The R-square value represents the proportion of variance in the dependent variable that is explained by the predictor variables in the model. It ranges from 0 to 1, with higher values indicating better explanatory power. R-square value. Refer to the model summary table in the regression output. Look for the R-square value, which represents the proportion of variance in the dependent variable that is explained by the predictor variables in the model. ANOVA table and coefficients table. Look for the ANOVA table in the regression output. The ANOVA table provides information on the overall significance of the regression model, including the F-value and associated P-value. Look for the coefficients table in the regression output. The coefficients table provides information on the individual coefficients for each predictive variable, including the standardized coefficient, beta, the unstandardized coefficient, b, and associated t-value and p-value. Validating the overall fitness of the model. Check the overall significance of the model by looking at the p-value in the ANOVA table. A significant p-value, usually less than 0.05, indicates that the model has some explanatory power. Check the goodness of fit of the model by looking at the R-square value in the model summary table. A higher R-square value indicates better explanatory power. Check the normality of the residuals by looking at a histogram or normal probability plot of the residuals. Residuals should be normally distributed around a mean of 0 with constant variance. Check for outliers or influential data points by examining a scatter plot of the residuals against the predicted values. Any points that are far away from the other points may be outliers or influential observations. 8. Uses of ANOVA and post hoc analysis after ANOVA. Analysis of variance, ANOVA, is a statistical technique used to compare the means of two or more groups to determine whether there are significant differences between them. It can be used to test hypotheses about the equality of population means in various fields such as business, social sciences, and engineering. Some of the common uses of ANOVA are as follows. Comparing the means of 3 or more groups, ANOVA can be used to determine whether there are significant differences between the means of 3 or more groups. Testing the effects of different factors, ANOVA can be used to test the effects of different factors, such as different levels of a treatment or different groups of subjects. Determining interactions between factors, ANOVA can also be used to determine whether there are interactions between different factors that affect the dependent variable. After conducting ANOVA, post hoc analysis can be performed to identify which groups differ significantly from one another. Some of the commonly used post hoc tests are Tukey's honestly significant difference, HSD. This test compares all possible pairs of group means to determine which ones are significantly different from each other. Bonferroni correction. This test adjusts the significance level of each comparison to control for the increased risk of type I error that occurs when multiple comparisons are made. Skeef's method. This test provides a conservative estimate of the significance of group differences and can be used when the assumption of equal variances is not met. Post hoc tests can help to identify which groups have significant differences, but they should be used with caution because they increase the risk of type I error. It is important to choose a post hoc test that is appropriate for the data and to report the results of the test along with the ANOVA results. From ANOVA SPSS output. Write the general form of null and alternate hypothesis for ANOVA. Procedures to infer the output. The general form of the null and alternative hypotheses for ANOVA are: null hypothesis, H0 there is no significant difference between the means of the groups being compared. Alternative hypothesis, there is a significant difference between the means of the groups being compared. To infer the output from an ANOVA in SPSS, you should follow these general procedures. Look for the F-value. The F-value represents the ratio of the variance between groups to the variance within groups. If the F-value is large, then it suggests that there is a significant difference between the means of the groups being compared. Check the p-value. The p-value is the probability of obtaining the observed F-value by chance, assuming that the null hypothesis is true. If the p-value is less than the significance level, usually 0.05, then we can reject the null hypothesis and conclude that there is a significant difference between the means of the groups being compared. Look at the means. If the null hypothesis is rejected, then you should look at the means of the groups being compared to determine which groups are significantly different from each other. You can use post hoc tests like Tukey's HSD or Bonferroni to conduct pairwise comparisons. Check assumptions. Before interpreting the ANOVA output, you should check that the assumptions of ANOVA have been met, including normality, homogeneity of variance, and independence. You can use diagnostic plots like histograms, normal probability plots, and scatter plots to check these assumptions. By following these procedures, you can interpret the output from an ANOVA in SPSS and make conclusions about the statistical significance of the differences between the means of the groups being compared. Parametric versus non-parametric tests, assumptions. Parametric tests and non-parametric tests are two types of statistical tests used to analyze data in different scenarios. Parametric tests are based on the assumption that the data follow a normal distribution, while non-parametric tests do not make any assumptions about the underlying distribution of the data. Assumptions of parametric tests. Normality, the data must follow a normal distribution. Homogeneity of variance, the variances of the groups being compared must be equal. Independence, the observations must be independent of each other. Examples of parametric tests include t-tests, ANOVA, and regression analysis. Assumptions of non-parametric tests. The data do not need to follow a normal distribution. The variances of the groups do not need to be equal. The observations must be independent of each other. Examples of non-parametric tests include Wilcoxon-Rank-Sum test, Mann-Whitney-U test, Kruskal-Wallis test, and Spearman's rank correlation. Non-parametric tests are often used when the assumptions of parametric tests are violated, or when the data are ordinal or categorical. However, non-parametric tests are generally less powerful than parametric tests, meaning that they may have lower statistical power to detect differences between groups. In summary, parametric tests assume that the data are normally distributed, while non-parametric tests make no assumptions about the distribution of the data. The choice of which test to use depends on the type of data and the assumptions that can be made about the data. It is important to check the assumptions of the chosen test before making any conclusions about the data. 11. When are non-parametric hypothesis testing methods preferred to parametric methods? Non-parametric hypothesis testing methods are preferred over parametric methods when one or more of the following conditions are met. Non-normal distribution of data. Non-parametric tests do not make any assumptions about the underlying distribution of the data, whereas parametric tests typically assume that the data follows a normal distribution. Therefore, non-parametric tests are preferred when the data does not meet the normality assumption. Small sample size. Parametric tests require a larger sample size to ensure that the assumptions of the test are met. Non-parametric tests, on the other hand, are less sensitive to sample size and can be used with smaller sample sizes. Outliers or extreme values. Non-parametric tests are less affected by outliers or extreme values in the data than parametric tests. Therefore, if there are outliers or extreme values in the data, non-parametric tests may be preferred. Ordinal data. Non-parametric tests can be used with ordinal data, whereas parametric tests require interval or ratio data. Therefore, if the data is in the form of rankings or categories, non-parametric tests may be preferred. Nonlinear relationships. Non-parametric tests can handle nonlinear relationships between variables, whereas parametric tests assume a linear relationship. Therefore, if the relationship between variables is nonlinear, non-parametric tests may be preferred. Overall, non-parametric tests are more robust to violations of assumptions and can be used in a wider range of situations than parametric tests. However, non-parametric tests may have less power than parametric tests when the assumptions of the latter are met. Unit 3. Data Science Definition, 3 marks. Data science is a multidisciplinary field that involves the use of statistical and computational methods to extract insights and knowledge from data. It combines skills from various domains such as statistics, mathematics, computer science, and domain-specific knowledge to analyze and interpret complex data sets. The ultimate goal of data science is to uncover hidden patterns and relationships in the data, which can be used to inform decision-making and solve real-world problems. Data science also involves the development of machine learning models and algorithms to automate the analysis of data and make predictions or recommendations based on the patterns observed in the data. The steps in building a data science model. There are several steps involved in building a data science model, and they can vary depending on the specific problem and data set. However, a general outline of the process includes: problem definition. Identify the problem you want to solve and define the objectives of the project. This step is crucial as it helps to narrow down the scope of the project and ensures that the model is built to address the specific problem. Data collection. Collect the relevant data from various sources, including databases, APIs, and external data sets. It is important to ensure that the data is reliable, clean, and properly formatted before proceeding to the next step. Data pre-processing. Clean, transform, and pre-process the data to ensure that it is ready for analysis. This step may involve data cleaning, feature selection, feature engineering, and data normalization. Model selection. Select the appropriate machine learning algorithm or model that is best suited for the problem at hand. This step involves evaluating different models and selecting the one that performs the best on the data set. Model training. Train the model on the training data set, using techniques such as cross-validation to ensure that the model is robust and not overfitting the data. Model evaluation. Evaluate the performance of the model on the validation or test data set. This step involves measuring the accuracy, precision, recall, and other performance metrics of the model. Model deployment. Deploy the model in a production environment, either as an API or as part of a larger software system. This step may involve integrating the model with other systems and ensuring that it is scalable and secure. Model monitoring and maintenance. Continuously monitor the performance of the model and make necessary updates and improvements to ensure that it remains effective and relevant. 3. Illustrate the CRISP data mining model for a specific industry. The CRISP-DM, Cross-Industry Standard Process for Data Mining, model is a widely used framework for data mining projects. It consists of 6 phases: business understanding, data preparation, modeling, evaluation, and deployment. Here is an example of how the CRISP-DM model can be applied to the healthcare industry. Business understanding. In this phase, the healthcare organization defines the problem they want to solve or the question they want to answer using data mining. For example, a hospital might want to reduce the number of patients who are readmitted within 30 days of discharge. Data understanding. In this phase, the healthcare organization gathers and examines relevant data. This may include data on patient demographics, medical history, medications, and readmission rates. The data is then analyzed to identify any missing values, anomalies, or inconsistencies. Data preparation. In this phase, the healthcare organization prepares the data for analysis. This may involve cleaning the data, selecting the relevant features, transforming the data into a suitable format for analysis, and splitting the data into training and testing sets. Modeling. In this phase, the healthcare organization develops and trains a predictive model to identify patients at risk of readmission. This may involve using techniques such as logistic regression, decision trees, or neural networks. The model is then evaluated on the testing set to determine its performance. Evaluation. In this phase, the healthcare organization evaluates the performance of the model and determines whether it meets the objectives set out in the business understanding phase. This may involve calculating metrics such as accuracy, precision, recall, and F1 score. Deployment. In this phase, the healthcare organization deploys the model in a production environment. This may involve integrating the model with the hospital's electronic medical record system or developing a standalone application for clinicians to use. The model is then continuously monitored and updated to ensure its effectiveness. Overall, the CRISP-DM model provides a structured approach to data mining projects in the healthcare industry, enabling organizations to leverage data to improve patient outcomes and reduce costs. 4. Importance of feature engineering. Feature engineering is a critical step in data science and machine learning that involves selecting, extracting, and transforming relevant features from raw data to improve the performance of predictive models. Here are some reasons why feature engineering is important. Improves model accuracy. The quality and relevance of the features used in a model have a significant impact on its accuracy. By selecting and engineering the right features, data scientists can improve the performance of their models and make more accurate predictions. Reduces overfitting. Overfitting occurs when a model is too complex and fits the training data too closely, leading to poor generalization to new data. Feature engineering can help reduce overfitting by selecting the most relevant features and removing noisy or irrelevant ones. Enables domain expertise. Feature engineering allows data scientists to leverage their domain knowledge and expertise to create features that are relevant and meaningful in the context of the problem they are trying to solve. Improves interpretability. Feature engineering can make models more interpretable by selecting features that are easy to understand and explain. This can help stakeholders and decision makers understand the factors that are driving the model's predictions. Enables transfer learning. Feature engineering can be used to extract features from pre-trained models and transfer them to new models, allowing data scientists to leverage existing knowledge and reduce the need for large amounts of labeled data. Overall, feature engineering is a critical step in the machine learning pipeline that can have a significant impact on the performance and interpretability of predictive models. It requires creativity, domain expertise, and a deep understanding of the problem at hand, and can lead to significant improvements in the accuracy and generalization of models. 5. Feature engineering techniques. Feature engineering is the process of selecting, transforming, and creating new features from raw data to improve the performance of machine learning models. Here are some commonly used feature engineering techniques. Scaling and normalization. This involves scaling numerical features to a specific range or normalizing them to have zero mean and unit variance. This technique can improve the performance of models that are sensitive to the scale of the input features, such as k-nearest neighbors and gradient descent-based algorithms. One-hot encoding. This technique is used to encode categorical features as binary vectors, with each category represented by a separate feature. This can improve the performance of models that require numerical input, such as linear regression and neural networks. Feature aggregation. This involves creating new features by aggregating or combining existing ones. For example, the average, minimum, and maximum of a set of related features can be computed and used as new features. Feature selection. This involves selecting a subset of the most relevant features to use in the model, based on criteria such as correlation, information gain, and mutual information. This can improve the performance of models by reducing overfitting and increasing interpretability. Feature extraction. This involves transforming high-dimensional data, such as images or text, into a low-dimensional feature space. This can be done using techniques such as principal component analysis, PCA, or latent semantic analysis, LSA. Time series feature engineering. This involves creating new features from time series data, such as rolling averages, moving windows, and lagged features. This can capture trends, seasonality, and other patterns in the data. Overall, feature engineering is a critical step in machine learning and requires creativity, domain knowledge, and an understanding of the problem at hand. By applying these techniques, data scientists can create more effective and efficient models that are better suited to the data and the problem they are trying to solve. 6. Supervised versus unsupervised learning algorithms. Supervised and unsupervised learning are two main categories of machine learning algorithms. Here is an overview of the differences between them and some commonly used algorithms in each category. Supervised learning. Supervised learning algorithms are trained on labeled data, where the input features are associated with corresponding target labels or outputs. The goal is to learn a mapping between input features and target labels that can be used to predict the target labels for new, unseen data. Some examples of supervised learning algorithms are linear regression. This is a regression algorithm that models the linear relationship between the input features and the target output. Logistic regression. This is a classification algorithm that models the probability of an input belonging to a specific class. Decision trees. This is a tree-based algorithm that recursively splits the data based on the input features, with each node representing a decision or feature. Random forests. This is an ensemble algorithm that combines multiple decision trees to improve performance and reduce overfitting. Unsupervised learning. Unsupervised learning algorithms are trained on unlabeled data, where the input features have no corresponding target labels or outputs. The goal is to learn patterns, structure, or relationships in the data that can be used for tasks such as clustering, dimensionality reduction, and anomaly detection. Some examples of unsupervised learning algorithms are k-means clustering. This is a clustering algorithm that groups similar data points into a specified number of clusters based on their proximity in feature space. Principal component analysis, PCA. This is a dimensionality reduction algorithm that transforms high-dimensional data into a low-dimensional space while preserving the maximum amount of variance. Anomaly detection. This involves identifying data points that are significantly different from the rest of the data, which can be useful for detecting fraud or anomalies in a system. Association rule mining. This involves discovering frequent patterns or co-occurrences in the data, which can be useful for tasks such as market basket analysis. Overall, the choice of a supervised or unsupervised learning algorithm depends on the type of data available and the task at hand. Supervised learning is useful when there is labeled data available and the goal is to predict a specific output, while unsupervised learning is useful when there is no labeled data available and the goal is to discover patterns or structure in the data. Overfit versus underfit models. Measures to overcome. Overfitting and underfitting are common problems in machine learning models. Here is an overview of what they are and some measures to overcome them. Overfitting. Overfitting occurs when a model fits the training data too closely, resulting in high variance and poor generalization performance on new, unseen data. Overfitting can happen when the model is too complex or when the training data is too small or noisy. Some measures to overcome overfitting include regularization. This involves adding a penalty term to the loss function that encourages the model to have smaller weights or fewer parameters, which can reduce overfitting. Cross-validation. This involves splitting the data into training and validation sets and using the validation set to evaluate the model's performance and tune hyperparameters. This can help prevent overfitting by providing a more accurate estimate of the model's generalization performance. Early stopping. This involves monitoring the validation loss during training and stopping the training when the validation loss starts to increase, which can prevent the model from overfitting the training data. Underfitting. Underfitting occurs when a model is too simple and fails to capture the underlying patterns in the data, resulting in high bias and poor performance on both training and test data. Underfitting can happen when the model is not complex enough or when the training data is insufficient. Some measures to overcome underfitting include increasing model complexity. This can involve adding more layers or nodes to a neural network, increasing the degree of a polynomial regression model, or using a more complex algorithm. Adding more features. This involves adding more input features or transforming existing features to better capture the underlying patterns in the data. Collecting more data. This can help the model learn the underlying patterns in the data and reduce the chance of underfitting. Overall, preventing overfitting and underfitting is crucial for building machine learning models that can generalize well to new, unseen data. By using techniques such as regularization, cross-validation, and early stopping for overfitting, and increasing model complexity, adding more features, or collecting more data for underfitting, data scientists can improve the performance and reliability of their models. Bias versus variance, measures to overcome them. Bias and variance are two important concepts in machine learning that are related to the accuracy and generalization ability of a model. Bias refers to the difference between the expected or average predictions of a model and the true values. High bias means that the model is too simplistic and underfits the data, while low bias means that the model is more complex and fits the data well. Variance, on the other hand, refers to the variability of model predictions for different training data sets. High variance means that the model is too sensitive to the specific data it was trained on and may overfit, while low variance means that the model is more robust and generalizes well to new data. Here are some measures to overcome bias and variance. Bias. To overcome bias, you can try to increase the complexity of the model by adding more features, using a more complex algorithm, or tuning the hyperparameters. You can also try to reduce the regularization strength or increase the number of iterations for the model to converge. Variance. To overcome variance, you can try to reduce the complexity of the model by removing some features, using a simpler algorithm, or tuning the hyperparameters to increase the regularization strength. You can also try to increase the size of the training dataset, or use techniques such as cross-validation or ensemble learning to reduce the variance. Bias-variance trade-off. It's important to find a balance between bias and variance, as reducing one can increase the other. One approach is to use regularization techniques such as L1, L2 regularization or dropout to reduce both bias and variance simultaneously. Another approach is to use ensemble methods such as bagging, boosting or stacking to combine multiple models and reduce the variance while keeping the bias under control. Data quality. The quality and quantity of data used for training the model is also crucial for overcoming bias and variance. You can try to collect more data or improve the quality of the existing data by cleaning, pre-processing, and normalizing it. In summary, overcoming bias and variance requires a combination of techniques, including selecting the right model, tuning the hyperparameters, using regularization, ensembling, and improving the quality of data. Unit 4. Naive Bayes algorithm and application. Naive Bayes is a classification algorithm based on Bayes' theorem with the assumption of independence between features. It is a simple and effective algorithm that is commonly used in text classification, spam filtering, and sentiment analysis. The algorithm works by calculating the probability of each class given a set of input features, and then selecting the class with the highest probability as the output. To calculate these probabilities, naive Bayes makes the following assumptions. Each input feature is independent of all the others. All input features are equally important in predicting the class. Naive Bayes comes in three variants, namely Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. These variants differ in the way they handle continuous, discrete, and binary features, respectively. Here are some common applications of naive Bayes. Text classification. Naive Bayes is widely used for text classification tasks such as spam filtering, sentiment analysis, and topic classification. In these applications, the algorithm is trained on a labeled dataset of text documents, and then used to classify new documents based on their content. Recommendation systems. Naive Bayes can be used in recommendation systems to predict whether a user will like a particular item or not. This is done by training the algorithm on a dataset of user-item interactions, and then using it to predict the probability of a user liking a new item based on their previous interactions. Medical diagnosis. Naive Bayes has been used in medical diagnosis to predict the probability of a patient having a particular disease based on their symptoms and other medical records. Fraud detection. Naive Bayes can be used to detect fraudulent transactions by analyzing the patterns and characteristics of previous fraudulent transactions and then predicting the probability of a new transaction being fraudulent based on these patterns. In summary, naive Bayes is a simple and effective classification algorithm that can be applied to a wide range of applications, particularly in text classification, recommendation systems, medical diagnosis, and fraud detection. Support vector machines and applications. Support vector machines, SVMs, are a popular classification algorithm that is used to find the best decision boundary between different classes of data. SVMs work by finding the hyperplane that maximizes the margin between the classes. The margin is defined as the distance between the hyperplane and the closest data points of each class. SVMs can be used for both linear and nonlinear classification tasks, depending on the choice of kernel function. Some common kernel functions used in SVMs are linear, polynomial, and radial basis function, RBF. Here are some common applications of SVMs. Image classification. SVMs have been widely used in image classification tasks such as object recognition, face detection, and only used in text classification tasks such as sentiment analysis, topic classification, and spam filtering. In these applications, the SVM is trained on a dataset of labeled text documents, and then used to classify new documents based on their content. Bioinformatics. SVMs have been used in bioinformatics to classify genes, predict protein structures, and identify disease markers. In these applications, the SVM is trained on a dataset of biological data, and then used to predict the properties of new data based on their features. Financial analysis. SVMs have been used in financial analysis to predict stock prices, detect credit card fraud, and identify trading strategies. In these applications, the SVM is trained on a dataset of financial data, and then used to make predictions based on the historical patterns of the data. In summary, SVMs are a powerful classification algorithm that can be applied to a wide range of applications, particularly in image and text classification, bioinformatics, and financial analysis. SVMs are effective in finding the best decision boundary between different classes of data and can handle both linear and nonlinear classification tasks. Decision tree algorithm and application, merits and demerits of decision tree algorithms. Decision tree is a popular machine learning algorithm used for classification and regression tasks. It works by recursively splitting the dataset into smaller subsets based on the most significant feature until a stopping criterion is met. The final result is a tree-like structure where each internal node represents a decision based on a feature and each leaf node represents a class or a value. Here are some common applications of decision trees. Predictive modeling. Decision trees are commonly used in predictive modeling tasks such as customer churn prediction, fraud detection, and loan approval. In these applications, the decision tree is trained on a labeled dataset and then used to predict the outcome of new instances. Medical diagnosis. Decision trees have been used in medical diagnosis to predict the probability of a patient having a particular disease based on their symptoms and medical history. Quality control. Decision trees can be used in quality control to identify the most important factors affecting product quality and to develop strategies to improve it. Merits of decision trees. Easy to understand and interpret, decision trees can be visualized and easily interpreted by humans, which makes them useful for explaining the reasoning behind the predictions. Can handle both categorical and numerical data. Decision trees can handle both categorical and numerical data, which makes them versatile in handling different types of data. Can handle missing data. Decision trees can handle missing data by using surrogate splits or imputation methods. Can handle nonlinear relationships. Decision trees can handle nonlinear relationships between the features and the outcome variable. Demerits of decision trees. Overfitting. Decision trees are prone to overfitting, which can lead to poor generalization performance on new data. Sensitivity to small variations in the data. Small variations in the data can lead to large changes in the structure of the decision tree, which can make it less robust. Biased towards features with many categories. Decision trees tend to be biased towards features with many categories, which can lead to overrepresentation of these features in the tree. Can be computationally expensive. Building a decision tree can be computationally expensive, particularly when the dataset is large or the tree is deep. In summary, decision trees are a popular and effective machine learning algorithm that can be applied to a wide range of applications, particularly in predictive modeling, medical diagnosis, and quality control. They are easy to interpret and can handle both categorical and numerical data. However, they are prone to overfitting and can be sensitive to small variations in the data, which can make them less robust. Gini index in decision tree algorithms. In decision tree algorithms, the Gini index, also called Gini impurity, is a metric that is used to measure the quality of a split in the dataset. It is a measure of how often a randomly chosen element from the dataset would be incorrectly classified if it were randomly labeled according to the distribution of labels in the subset. The Gini index ranges from 0 to 1, with 0 indicating that all the elements in the subset belong to the same class and 1 indicating that the elements are equally distributed among all the classes. A lower Gini index value implies a better split as it indicates that the resulting subsets are more homogeneous. In decision tree algorithms, the Gini index is used to determine the optimal split in the dataset by minimizing the impurity in each subset. The split with the lowest Gini index value is chosen as the best split. The formula for calculating the Gini index is as follows. Gini index is equal to 1, pi, 2, where pi is the probability of an element in the subset being classified to a particular class. Overall, the Gini index is an important metric in decision tree algorithms as it helps to determine the best split in the dataset, which in turn leads to the creation of more accurate and efficient decision trees. 5. Logistic regression and its application. Logistic regression is a statistical method used to analyze the relationship between a binary or categorical dependent variable and one or more independent variables. It is commonly used for classification problems, where the goal is to predict the probability of an event occurring based on a set of predictor variables. The logistic regression model works by using a sigmoid function to map the input variables to a probability value between 0 and 1, which can be interpreted as the probability of the event occurring. The sigmoid function is defined as p kiss smiley is equal to 1 plus x, z, where p, kiss smiley is the probability of the event occurring, Z is the linear combination of the input variables and their corresponding coefficients. Logistic regression is widely used in various fields, including healthcare, marketing, and finance. Some examples of its applications are disease diagnosis. Logistic regression can be used to predict the likelihood of a patient having a particular Considering the logistic regression model output in SPSS, answer the following question. Infer the omnibus test results. Infer Wald statistic. What is the use of Hosmer-Lamassoure test results in logistic regression? Write the general logistics regression model. Just procedures to write inference of output. Assuming you have a logistic regression output in SPSS, here are the steps to answer your questions. Infer the omnibus test results. The omnibus test of model coefficients is a statistical test that assesses the overall significance of the logistic regression model. In SPSS, the omnibus test is represented by the model chi-square value. To infer the omnibus test results, follow these steps. Look for the model summary table in the output. Check the model chi-square value and its corresponding degrees of freedom, df. Calculate the p-value for the chi-square test using a chi-square distribution table or calculator. If the p-value is less than the significance level, infer Wald statistic. The Wald statistic is a measure of the significance of each individual predictive variable in the logistic regression model. In SPSS, the Wald statistic is represented by the sig column in the coefficients table. To infer the Wald statistic, follow these steps. Look for the coefficients table in the output. Check the sig column for each predictive variable and its corresponding coefficient. If the p-value, sig, is less than the significance level, usually 0.05, we can reject the null hypothesis and conclude that the predictive variable is significant. What is the use of Hosmer-Lamassoure test results in logistic regression? The Hosmer-Lamassoure test is a goodness of fit test that assesses how well the logistic regression model fits the observed data. In SPSS, the Hosmer-Lamassoure test is performed using the Hosmer and Lamassoure test option in the Model Fit tab. The test splits the data into several groups based on predicted properties. The purpose of the test is to determine whether the model is well calibrated. Write the general logistic regression model. The general logistic regression model can be written as follows. Logit P is equal to ln P 1 dash P is equal to B0 plus B1 x1 plus B2 x2 plus Bk asterisk xk, where P is the probability of the event occurring, x1 x2 xk are the predictor variables, b0 b1 b2 bk are the regression coefficients, and logit is the natural logarithm of the odds ratio. The goal of logistic regression is to estimate the values of the regression coefficients, b0 b1 b2 bk, that best predict the probability of the event occurring. Application of clustering algorithms. Clustering algorithms are used in various applications where we need to group similar objects or data points together. Some common applications of clustering algorithms are customer segmentation. Clustering algorithms can be used to segment customers based on their purchase behavior, demographics, or other characteristics. This can help businesses to tailor their marketing strategies and products to specific customer groups. Image segmentation. Clustering algorithms can be used to segment images into different regions based on their color, texture, or other features. This can be useful in computer vision applications, such as object recognition or tracking. Anomaly detection. Clustering algorithm. Document clustering. Clustering algorithms can be used to group similar documents together based on their content or other features. This can be useful in information retrieval or text classification applications. Recommendation systems. Clustering algorithms can be used to group users or items together based on their preferences or other characteristics. This can be useful in building recommendation systems, such as those used by e-commerce websites or streaming services. Genetic analysis. Clustering algorithms can be used to group genes together based on their expression patterns. This can be useful in genetic research, such as identifying genes that are associated with particular diseases. Overall, clustering algorithms are a powerful tool for discovering structure in data and identifying groups or patterns that may not be apparent by simply looking at the data. Purpose of factor analysis. The purpose of factor analysis is to identify underlying factors or latent variables that explain the correlations among a set of observed variables. It is a statistical technique or dimensions, while retaining as much information as possible. Factor analysis is commonly used in the field of psychology, social sciences, and market research to uncover the underlying structure of complex data sets. The main purposes of factor analysis are: data reduction. Factor analysis is used to reduce the number of variables in a data set while retaining as much information as possible. This can be useful in situations where variable selection. Factor analysis can be used to select a subset of variables that are most closely related. Hypothesis testing. Factor analysis can be used to test hypotheses about the underlying structure of a data set. For example, researchers may hypothesize that certain variables are related to a specific factor, and factor analysis can be used to test this hypothesis. Construct validity. Factor analysis can be used to assess the construct validity of a measurement instrument. By identifying the underlying factors, researchers can assess whether the instrument is measuring what it is intended to measure. Overall, factor analysis is a powerful tool for identifying underlying factors and reducing the complexity of a data set, and it can be used from the given SPSS factor analysis output. How to infer KMO and Bartlett's test table. Infer the total infer the rotated to infer the KMO and open the scroll down in the row to infer the total variance table from the SPSS to in the Kaiser-Meyer-King measure of sampling adequacy row, check the value in the overall column. This value indicates the overall sampling adequacy for the factor analysis. Generally, values greater than 0.6 are considered acceptable. In the row labeled Bartlett's test of sphericity, check the significance value in the sig column. If the value is less than 0.05, this indicates that the correlations between the variables are sufficiently different from 0 to justify factor analysis. To infer the total variance table from the SPSS factor analysis output, follow these procedures. Scroll down to the section labeled Total Variance Explained in the output. Look at the Initial Eigenvalues table, which displays the eigenvalues for each factor before rotation. These values indicate the amount of variance explained by each factor. Look at the Total Variance Explained table, which shows the cumulative proportion of variance explained by each factor. This can help you determine the number of factors to retain in the analysis. To infer the rotated component matrix considering a cutoff value from the SPSS factor analysis output, follow these procedures. Scroll down to the section labeled Rotated Component Matrix in the output. Look at the values in the cells of the table to see the factor loadings for each variable. These values represent the correlation between the variable and the factor. Apply a cutoff value to determine which variables have strong loadings on each factor. A common cutoff value is 0.3, but this may vary depending on the specific research question and data characteristics. Variables with factor loadings greater than the cutoff value can be interpreted as strongly related to the corresponding corresponding factor. 10. Design of confusion matrix with given data. Calculation of the overall accuracy of the test, precision and recall values, false alarm rate, to design, determine, count, fill, vertical, actual, vertical bar dash dash, to calculate the precision and recall value. Precision is equal to TP plus FP. Recall is equal to TP plus FN. The false alarm, for example, overall, a confusion matrix, hierarchical clustering versus k-means clustering. Hierarchical clustering and k-means clustering are two popular unsupervised machine learning algorithms used for clustering and grouping similar data points. However, there are some key differences between these two methods. Hierarchical clustering involves creating a hierarchy of clusters, where each data point is initially assigned to its own cluster. These clusters are then successively merged together, based on their similarity, until all the data points are in a single cluster. This process can be represented using a dendrogram, which is a tree-like diagram that shows how the clusters were merged. K-means clustering, on the other hand, involves partitioning the data into a predefined number of clusters, where the number of clusters is specified by the user. The algorithm starts by randomly assigning data points to the specified number of clusters, and then iteratively refines the assignments until the clusters are optimized. The K in K-means refers to the number of clusters. Here are some of the key differences between hierarchical clustering and K-means clustering. Hierarchical clustering is more flexible than K-means clustering, as it does not require a predefined number of clusters. Hierarchical clustering can be either agglomerative, bottom-up, or divisive, top-down, while K-means clustering is always agglomerative. In hierarchical clustering, the distance between clusters is used to determine which clusters to merge together, while in K-means clustering, the centroids of the clusters are used to determine which data points belong to each cluster. Hierarchical clustering can be computationally intensive for large data sets, as the dendrogram needs to be constructed, while K-means clustering is generally faster and more scalable. Overall, the choice between hierarchical clustering and K-means clustering depends on the specific problem at hand and the nature of the data. Hierarchical clustering is more suitable when the number of clusters is unknown or when the data has a hierarchical structure, while K-means clustering is more suitable when the number of clusters is known and the data is not hierarchical. Insights that can be gained from K-means cluster SPSS output, procedures. Sure. Here are some insights that can be gained from the K-means cluster analysis output in SPSS. Number of clusters, cluster centroids. The output will also provide information about the centroid of each cluster. The centroid, cluster membership. The output will also provide information about the membership of each data point in each cluster. By examining the cluster membership, you can identify which data points belong to each cluster and gain insights into the similarities and differences between the data points in each cluster. Cluster profiling. SPSS allows you to generate cluster profiling tables which provide descriptive statistics for each cluster. You can use these tables to gain a deeper understanding of the characteristics of each cluster and to identify any patterns or cluster visualization. SPSS also allows you to visualize the clusters using scatter plots, which can help you to gain insights into the relationship. Overall, the insights that can be gained from the K-means cluster analysis output in SPSS can help you to identify natural groupings within your data, to understand the characteristics of each cluster, and to make decisions based on the insights that you. Regularization in machine learning. Regularization is a technique used in machine learning to prevent overfitting, which is when a model is too complex and fits the training data too well, but does not generalize well to new data. Regularization methods add a penalty term to the loss function of the model to discourage it from fitting the training data too closely and to encourage it to generalize better to new data. There are two main types of regularization techniques used in machine learning. L1 regularization, lasso. In L1 regularization, the penalty term added to the loss function is the absolute value of the coefficients of the model. L1 regularization is used when we have a large number of features, and we want to select the most important ones. It tends to produce sparse models, where many of the coefficients are set to 0. L2 regularization, RIG. In L2 regularization, the penalty term added to the loss function is the squared value of the coefficients of the model. L2 regularization is used when we want to prevent overfitting by reducing the size of the coefficients of the model. It tends to produce models with smaller coefficients that are more evenly distributed across all features. Regularization is typically applied to linear regression models, logistic regression models, and neural networks, but it can be applied to other types of models as well. The strength of the regularization penalty is controlled by a hyperparameter, which needs to be tuned to find the best balance between overfitting and underfitting. Regularization is a powerful technique in machine learning that can help to improve the performance and generalization of models, especially when working with high-dimensional datasets with many features. Neural networks and application. Neural networks are a type of machine learning algorithm that can be used for a wide range of applications, including image and speech recognition, natural language processing, predictive analytics, and anomaly detection. In image recognition, neural networks can be used to identify objects, people, and other features within images. For example, they can be used to identify whether an image contains a cat or a dog, or to identify faces in a crowd. In speech recognition, neural networks can be used to transcribe spoken words into text, which can be useful in a variety of applications, such as speech-to-text software and virtual assistants. In natural language processing, neural networks can be used to analyze text and understand its meaning, which can be used for tasks such as sentiment analysis, language translation, and chatbots. In predictive analytics, neural networks can be used to make predictions about future outcomes based on historical data, which can be useful in fields such as finance, marketing, and healthcare. In anomaly detection, neural networks can be used to identify unusual patterns or outliers in data, which can be useful in identifying fraud, security threats, or other unusual behavior. Overall, neural networks are a powerful tool for a wide range of applications, and their versatility makes them a valuable tool in many different fields. NLP brief description and definition. Natural language processing, NLP, is a field of study that focuses on the interactions between human language and computers. NLP aims to develop algorithms and techniques that enable computers to understand, interpret, and generate natural language text, allowing for more effective communication between humans and machines. NLP involves a variety of subfields, including computational linguistics, machine learning, and computer science. Some of the tasks that NLP can perform include text classification and categorization, sentiment analysis, information retrieval and extraction, machine translation, question answering, speech recognition and synthesis. NLP techniques involve the use of statistical and machine learning models to analyze and understand natural language text. This typically involves breaking down text into smaller units, such as words or phrases, and analyzing their meanings and relationships in context. NLP is used in a wide range of applications, including chatbots, virtual assistants, sentiment analysis, and machine translation, and is becoming increasingly important as more and more data is generated in natural language form. Reinforcement learning. Reinforcement learning is a type of machine learning that involves training an agent to interact with an environment in order to learn how to make decisions that maximize a cumulative reward. In other words, the agent learns through trial and error, receiving feedback in the form of rewards or penalties as it takes actions within the environment. Reinforcement learning involves three main components: the agent, the environment, and the reward function. The agent is the entity that takes actions within the environment, while the environment is the context in which the agent operates. The reward function specifies the goals and objectives of the agent, providing feedback in the form of rewards or penalties based on the agent's actions. Reinforcement learning algorithms typically involve a process called policy optimization, in which the agent learns to adjust its behavior over time in order to maximize the cumulative reward. This may involve exploration, in which the agent takes random or novel actions in order to learn about the environment, as well as exploitation, in which the agent takes actions based on its current knowledge in order to maximize the expected reward. Reinforcement learning has been applied to a wide range of applications, including robotics, game playing, and autonomous vehicles. One notable example is the use of reinforcement learning by DeepMind to train agents to play complex games like Go and chess at a superhuman level. Recommender systems. Recommender systems are a type of information filtering system that provide personalized recommendations to users based on their preferences, past behavior, and other data. These systems are commonly used in e-commerce, entertainment, and social media platforms to suggest products, services, or content to users that they are likely to be interested in. There are two main types of recommender systems. Collaborative filtering. This approach involves analyzing user behavior and preferences to identify patterns and similarities among users. Based on these patterns, the system can then recommend items to users that other similar users have shown interest in. Collaborative filtering can be either user-based or item-based, depending on whether the system looks for similar users or similar items. Content-based filtering. This approach involves analyzing the characteristics and features of items, such as their genre, author, or keywords, and recommending items to users that are similar to items they have liked in the past. Content-based filtering does not require knowledge about other users' behavior and preferences, making it useful in situations where user data is sparse or unavailable. Recommender systems typically use machine learning algorithms to analyze user data and generate recommendations. Some common techniques used in recommender systems include matrix factorization, clustering, and neural networks. Recommender systems have become increasingly important as the amount of data generated by users has grown, making it difficult for users to find relevant items among a large number of options. By providing personalized recommendations, recommender systems can help users find items they are interested in more easily, leading to increased engagement and customer satisfaction. Content-based filtering versus collaborative filtering. Content-based filtering and collaborative filtering are two main approaches used in recommender systems to provide personalized recommendations to users. Here is a comparison of the two methods. Content-based filtering analyzes the characteristics and features of items, such as genre, author, or keywords, and recommends items that are similar to items the user has liked in the past. Does not require knowledge about other users' behavior and preferences. Can be useful in situations where user data is sparse or unavailable. May suffer from the echo chamber problem, where users are only recommended items that are similar to what they have already consumed. Collaborative filtering analyzes user behavior and preferences to identify patterns and similarities among users, and recommends items that similar users have shown interest in. Can be either user-based or item-based, depending on whether the system looks for similar users or similar items. Requires a large amount of user data to be effective. Can suffer from the cold start problem, where new users or items do not have enough data to be effectively recommended. Both methods have their advantages and disadvantages, and the choice between them depends on the specific application and available data. In general, content-based filtering is useful when user data is limited or when users have highly individualized preferences, while collaborative filtering is more effective when there is a large amount of user data available and when users have similar preferences. In practice, many recommender systems use a combination of both methods to provide more accurate and effective recommendations. Hybrid recommenders. Hybrid recommenders are a type of recommender system that combines multiple recommendation techniques to provide more accurate and effective recommendations to users. Hybrid recommenders typically leverage the strengths of different recommendation techniques and use a variety of data sources to generate recommendations. For example, a hybrid recommender might combine content-based filtering, collaborative filtering, and demographic data to provide personalized recommendations. This approach can help address some of the limitations of individual recommendation techniques and provide more accurate and diverse recommendations. There are several benefits to using hybrid recommenders, including increased accuracy. By combining multiple recommendation techniques, hybrid recommenders can provide more accurate and relevant recommendations to users. Addressing limitations of individual techniques, each recommendation technique has its own strengths and weaknesses. By combining multiple techniques, hybrid recommenders can address some of the limitations of individual techniques. Better coverage. By using multiple data sources, hybrid recommenders can provide recommendations for a wider range of items and users. Flexibility. Hybrid recommenders can be tailored to specific applications and data sources, allowing for greater flexibility in providing recommendations. Hybrid recommenders can be challenging to implement, as they require integrating multiple recommendation techniques and data sources. However, they have become increasingly popular in recent years, particularly in e-commerce and content recommendation systems, where accuracy and personalization are critical for customer engagement and satisfaction. 7. Techniques for analysis of time series data. Time series data analysis is the process of studying data that is collected at regular intervals over time. This type of data can be found in various fields, such as finance, economics, healthcare, and environmental science. Here are some techniques commonly used for the analysis of time series data. Descriptive statistics. This technique involves computing summary statistics, such as mean, standard deviation, and variance, to describe the patterns and trends in the data. Trend analysis. This technique involves examining the overall direction and magnitude of the data over time. Trend analysis can be conducted visually through time series plots or statistically using techniques such as regression analysis. Seasonality analysis. This technique involves identifying patterns and trends that repeat at fixed intervals, such as daily, weekly, or monthly patterns. Seasonality analysis can be conducted visually through seasonal plots or statistically using methods such as Fourier analysis. Autocorrelation analysis. This technique involves examining the correlation between the data at different time points. Autocorrelation analysis can help identify patterns and trends that repeat at fixed intervals and can be used to model and forecast future trends. Time series decomposition. This technique involves separating a time series into its underlying components, such as trend, seasonality, and random variation. Time series decomposition can help identify patterns and trends that are not readily apparent in the raw data. Forecasting. This technique involves using statistical models to predict future trends and patterns in the data. Forecasting can be based on historical trends and patterns, as well as external factors such as economic indicators or weather patterns. Machine learning techniques. Machine learning techniques, such as neural networks, support vector machines, and decision trees, can also be used for time series data analysis. These techniques can help identify patterns and relationships in the data and can be used for forecasting and prediction. In summary, the techniques used for time series data analysis depend on the nature of the data and the specific goals of the analyst. Working of different types of recommender systems. There are several types of recommender systems, each with its own way of working. Content-based, collaborative, knowledge-based filtering. This type of recommender system relies on user-provided explicit data about their preferences, such as ratings or reviews, and uses that data to provide personalized recommendations. Knowledge-based filtering can be useful in situations where user data is limited or when users have highly individualized preferences. Hybrid recommender systems. These systems combine multiple recommendation techniques to provide more accurate and effective recommendations to users. Hybrid recommender systems can leverage the strengths of different recommendation techniques and use a variety of data sources to generate recommendations. Context-aware recommender systems. This type of recommender system takes into account contextual information, such as time, location, and weather, when making recommendations. Context-aware recommender systems can provide more personalized and relevant recommendations by taking into account the specific circumstances of the user. In summary, each type of recommender system has its own way of working and can be effective in different situations. Content-based filtering is useful when user data is limited or when users have highly individualized preferences, while collaborative filtering is more effective. Random forest algorithm, advantages and disadvantages. Random forest is a machine learning algorithm used for both classification and regression tasks. It is an ensemble method that combines multiple decision trees to make predictions. Here are some of the advantages and disadvantages of using the random forest algorithm. Advantages. Random forest is highly accurate and can handle a large number of input variables. It can handle missing data and maintain accuracy even if there are missing values in the input variables. It can handle both categorical and continuous variables. It is resistant to overfitting, which occurs when a model is too complex and performs well on the training data but poorly on the test data. It can provide measures of feature importance, which can be useful in understanding the relationships between the input variables and the output variable. Disadvantages. Random forest can be slow and require a large amount of memory to run, especially when dealing with a large number of input variables. The output of the model can be difficult to interpret, as the decision-making process is spread across multiple decision trees. Random forest may not perform well on small datasets, as there may not be enough data to build a sufficient number of decision trees. It can be difficult to tune the hyperparameters of the model, such as the number of trees, tree depth, and number of variables to include in each split. Random forest is not suitable for sequential data, as the order of the input variables does not matter and the algorithm assumes that each observation is independent of the others. In summary, random forest is a powerful machine learning algorithm that can handle a wide range of input variables, is resistant to overfitting, and can provide measures of feature importance. However, it can be slow and memory intensive, and its output may be difficult to interpret. Additionally, it may not perform well on small datasets or sequential data. Deep learning models are a subset of machine learning models that are based on artificial neural networks, which are composed of layers of interconnected nodes or neurons. Here are some of the most common types of deep learning models. Convolutional neural networks, CNNs. CNNs are primarily used for image recognition and processing tasks. They have multiple layers of convolutional and pooling operations that extract features from the input image. Recurrent neural networks, RNNs. RNNs are used for sequence prediction tasks, such as speech recognition or language translation. They have loops that allow them to process sequences of data, and can remember information from previous inputs. Long short-term memory, LSTM, networks. LSTMs are a type of RNN that are designed to address the problem of vanishing gradients in traditional RNNs. They have additional memory cells that allow them to remember information for longer periods of time. Autoencoders. Autoencoders are used for unsupervised learning tasks, such as image compression or anomaly detection. They consist of an encoder and a decoder network, and are trained to reconstruct the input data. Generative adversarial networks, GANs. GANs are used for generative tasks, such as image synthesis or text generation. They consist of a generator network and a discriminator network that compete against each other in a game-like fashion. Deep belief networks, DBNs. DBNs are used for unsupervised learning tasks, such as feature extraction or data pre-processing. They have multiple layers of restricted Boltzmann machines, RBMs, that learn to represent the input data in a hierarchical manner. Advantages of deep learning models. Deep learning models can learn complex patterns in data and can achieve state-of-the-art performance in many tasks. They can handle a large number of input variables and can learn from high-dimensional data. Deep learning models are scalable and can be trained on large datasets using parallel computing techniques. They can be used for a wide range of tasks, including image and speech recognition, natural language processing, and anomaly detection. Disadvantages of deep learning models. Deep learning models require a large amount of training data and can be computationally expensive to train. They can be difficult to interpret, and the decision-making process is often opaque. Deep learning models can suffer from overfitting, where the model performs well on the training data but poorly on new data. They require significant expertise to design and optimize, and tuning the hyperparameters can be challenging. In summary, deep learning models are a powerful class of machine learning models that can handle complex patterns in data and achieve state-of-the-art performance in many tasks. However, they can be computationally expensive to train, difficult to interpret, and prone to overfitting. Bagging and boosting ensemble methods. Bagging and boosting are two popular ensemble methods in machine learning that combine multiple models to improve predictive performance. Bagging stands for bootstrap aggregating. It is a technique in which multiple models are trained on different subsets of the training data. These models are then combined to make a final prediction. The subsets of data are selected randomly with replacement, which allows the same data points to be selected multiple times. This method is often used with decision tree models, where each tree is trained on a subset of the data and then the results are averaged to make a final prediction. Advantages of bagging. Reduces overfitting by reducing variance of the individual models. Can improve stability and robustness of the model. Disadvantages of bagging. Can increase the computational cost, as multiple models need to be trained. Can make the model more complex and difficult to interpret. Boosting. Boosting is a technique in which multiple models are trained sequentially, with each subsequent model focused on improving the performance of the previous model. The goal of boosting is to combine multiple weak models into a strong model. Weak models are models that are slightly better than random guessing. Boosting algorithms assign weights to each training instance, with the weights changing as the models are trained. In each iteration, the algorithm focuses on the instances that were misclassified by the previous models, with more weight assigned to these instances. Advantages of boosting. Can improve the accuracy of the model by reducing bias and increasing the model's ability to capture complex patterns in the data. Can be less computationally expensive than bagging, as it focuses on improving the performance of a single model. Disadvantages of boosting. Can increase the risk of overfitting, as the models are trained sequentially and the weights assigned to instances can lead to overemphasizing certain data points. Can be sensitive to noisy data, as the algorithm may assign too much weight to outliers. In summary, bagging and boosting are two ensemble methods in machine learning that can improve predictive performance by combining multiple models. Bagging reduces variance and can improve stability, while boosting reduces bias and can capture complex patterns in the data. Both methods have advantages and disadvantages that should be considered when choosing the appropriate method for a given problem. Steps in productionizing machine learning models. Productionizing machine learning models refers to the process of deploying a trained machine learning model into a production environment where it can be used to make predictions on real-world data. The following are some steps involved in productionizing machine learning models. Data preparation. The first step in productionizing a machine learning model is to prepare the data that will be used for training and testing the model. This involves cleaning the data, transforming it into a format that the model can use, and splitting it into training and testing sets. Model training and validation. Once the data is prepared, the model can be trained and validated using the training and testing sets. This involves selecting an appropriate algorithm, tuning the hyperparameters, and evaluating the model's performance on the testing data. Model deployment. After the model has been trained and validated, it can be deployed into a production environment. This involves selecting a platform or infrastructure to host the model and deploying the model onto that platform. Model monitoring. Once the model has been deployed, it is important to monitor its performance over time to ensure that it is still accurate and providing value. This involves tracking metrics such as accuracy, precision, recall, and F1 score, and identifying any issues that may arise. Model updating. As new data becomes available or the model's performance degrades over time, it may be necessary to update the model. This involves retraining the model with new data, fine-tuning the hyperparameters, and deploying the updated model into production. Integration with other systems. Finally, the model needs to be integrated with other systems or applications that will use its predictions. This involves designing an interface or API that can be used to access the model's predictions and integrating the model with other software systems. In summary, productionizing machine learning models involves preparing the data, training and validating the model, deploying it into a production environment, monitoring its performance, updating it as necessary, integrating it with other systems, and maintaining it over time. Each of these steps is critical for ensuring that the model is accurate, reliable, and providing value in a production setting. 13. Applications of data science in various industries. Data science has become increasingly important in many industries as organizations seek to gain insights and make better decisions based on data. Some applications of data. Healthcare. In healthcare, data science is being used to develop predictive models to identify patients who are at finance. In finance, data science is being used to develop retail. In retail, data science is being used to analyze customer data to identify buying patterns. Manufacturing. In manufacturing, data. Energy. In the energy industry, data science is being used to optimize energy production, reduce energy consumption. Transportation. In the transportation industry, data science is being used to optimize routes. In summary, data science is being used in a wide range of industries to improve decision-making, optimize operations, and improve customer experiences. As the importance of data-driven decision-making continues to grow, the role of data science in industry is likely to become even more important.